So gradient descent is one of the most problematic optimization problems in machine learning to understand for many machine learning students as well as people who want to get into data science, and for a good reason. Everyone makes it sound ultra complicated and super hard when in reality it's really not that difficult. It's just some basic steps that we need to take for the algorithm to converge and solve the problem efficiently. So in this video, I'll attempt to explain to you how gradient descent works and how you can implement it practically in your own algorithms and problems. So yeah, without wasting any more time, let's move on to the blackboard where we can understand it properly. So let us begin. In order to understand gradient descent, let's take a very simple algorithm to solve. So let's take least squares or the line of best fit. So we'll take these squares. Now it is also popularly called as linear regression, if you know it by that name. So the equation for least squares is y hat equals to wx plus b. Now, what are all these terms? Now, over here, y is nothing but the prediction that you need to find out. X is your dependent variable, and w is the weight or the weights, and b is nothing but bias. Now, if we were to plot a line, they all would look something like this. So now these are all the data points that I have. Okay, and now the line of best fit would look something like maybe like this. Okay, so now in order to see what all our like values are, now this line is nothing but the y hat, that is the prediction that we need to calculate. This little point over here, this intersection, this is nothing but the bias. Okay, and now the slope of the line, that is the angle on which the line needs to be on, is nothing but the weight of the line. Those are the weights that we need to find out. So the weights or the slope of the line that determine on which angle the line needs to be. So both by the combination of w as well as b, we find out where the line needs to be. So let's say the w and b. So let's say the value of w is some 0.7 and the value of b is some 0.2, and that will give me a line which is this. Now, if I were to change these values, the line might be, something like this, or something like this, or maybe this, or this. There can be many different lines over this, depending on what values of W and B we use. So, like if you didn't get it by now, we need to find out the right values for both W as well as B in order to find this line of best fit, right? So that is our ultimate goal, and we will achieve that using gradient descent. So let's see how we can do that. Okay, so now let's say that you have these data points over here, and then using some random value for both W and B. So let's just write random values over here. So just by using some random values, you got this line. Now, like we can tell just by looking at the line that it's not the line of best fit. But for our convenience sake, let's just say this is the first line that we got, okay? By using the random values for W as well as B, like the weights and biases. And these don't need to be random values. They can also be zeros, like if you want. So by using either random values or zero, we got this line of best fit or some other line or, something like that. So maybe just say this is our starting point. Now, to solve any problem in machine learning, what we need to do is we need to calculate the error and then we need to reduce the error. That's how it works, right? So let's find out the error. Now, in order to find the error, so we have one formula which is y minus y hat. Okay, so this is nothing but the actual value and this is the predicted value, right? So like the actual value is 250 and the predicted value is 150. The error will be 100. So that is how we calculate the error. So we need to calculate error not just for one point but for all these points. So this is the actual point and this over here is the error between the actual and the predicted point. Now similar to all of these points, so like the error, just by looking at it we can say that the error is pretty high. So we need to find out the error for all the points. So in order to find the error for all the point, we have something called as a cost function that can be a j or c, anything, there are many types of conventions, but you can use j or c. So it is 1 by n, that is for all the points, into summation of I from 1 all the way till n, that is for all the data points. You need to find y minus y hat the whole square. And the reason we are squaring is because we need to take care of the negative values. So for these values here, we'll get a positive term, but for these values, we'll get a negative term. And to handle that, we're just squaring, and then we are dividing by the number of data points. So this formula is nothing but MSE, or mean squared error. Okay. So by using mean squared error, this is our cost function, by the way. We are calculating the error between all these data points. So this is our cost function. Now comes the part of reducing the error. How can we reduce the error? Now it is quite obvious that when we calculate the error for these data points, the error will be very high. Correct? Now, of course, we'll use this formula, and but just by looking at this line, we can say that the error will be pretty high. Now, how can we reduce this line? So that's where gradient descent comes in. Okay, so this is a cost function, right? Now we can just rewrite it as something like this. So we can follow the same thing, but instead of y hat, we can actually write y hat equals to wx plus p, because this is the equation of the line. This is, we just replaced y hat with this, and then again we put the whole square so that we avoid the negative terms. So now comes the part of gradient. Now we need to take the derivatives with respect to both weights as well as biases. And then we keep reducing further and further until we get the right value. So let's not get ahead of ourselves. Let's first of all take the derivative with respect to the weights. So we'll just say dj by dw equals to, now I actually written down the derivative. It will be 1 by n into summation of I from 1 till n. That will be minus 2xi into yi minus wxi plus b. So now you need to take the derivative with respect to w in this case, and then if you take the derivative with respect to w, 2 will come over here, and then the negative sign will come over here as well, and then you'll have the x as well, and you can avoid the I just wrote it for one single data point, but you can avoid the I. So now since x is with y, with since x is with w, we'll put it over here as well, and then this will be the equation. So basically we're just taking a simple derivative. That's nothing complicated really. We're just taking a partial derivative with respect to w. So that's all we did over here in this step, and then we got this over here, and then we'll do the same. We'll further reduce it. We'll just say 1 by n into summation of I from 1 all the way to n. We'll say minus 2xi into yi minus, again we can reduce this term, right? We can again reduce this term as yi hat. Now, in order to get rid of this minus sign, we can just do something like this. 2xi equals to yi hat minus yi. So this will be the formula for dw, not the formula. This will be the equation for dw. This is the derivative with respect to w. So we got 1 by n into summation of I from 1 till n, 2xi into yi hat minus yi. So this is our equation. So let's just call this equation 1 and keep this in mind. Now we'll do the same thing, except we'll take the derivative with respect to w. So let's do that. So I written the cost function again. Now let us do the same thing. We can just rewrite this quickly as I from 1 till n by minus, instead of y hat, we can just write wx plus p. And then again we'll square it. Now, instead of taking the derivative with respect to the weights, let's take the derivative with respect to the biases this time. So it will be 1 by n into summation of I from 1 till n, and here it will be minus 2 into y minus wx plus p, and that's all. Now, since we are taking the derivative with respect to p, and p has a constant term attached with it, there will be nothing attached with 2. So basically, again, taking the derivative, nothing else. So if you're having difficulty in understanding how I took the derivatives, you can just maybe take a quick we can watch a quick tutorial on how to take the derivatives, because that's all I'm doing here, nothing complicated. So now that I've taken the derivative with respect to b as well, we can further simplify these terms as summation of I from 1 till n minus 2 into y minus, again I can rewrite this as y hat, and then again, in order to get rid of this minus sign, I'll just do this will be y hat minus y. So this will be my derivative with respect to b. Okay, so now I'm writing this as equation number 2. So keep this in mind. So in the previous one we got the dw, and then over here we got the db. So we got both of these. Okay, now we have both of these terms. Now let's move on further. Okay, so now I've written something over here called as the update rules. Now, what are these update rules? Now, after every iteration, you have to update your weights as well as biases, because if you keep taking the same values, then you will get the same line, right? There is no point in taking the same values. You need to update your W as well as your B, that is your weights as well as your biases, and you can do that using the simple formula, which is W, that is weights minus alpha into derivative of W, dW. And now this alpha is nothing but the learning rate. Now do not get confused about what the learning rate is. Learning rate is just some value you will specify, and that will determine how fast your gradient will move across the across the line. So that is nothing but the learning rate. Now if the learning rate, let's say, is 0.0001, that is like it's very low, so the gradient will be very low, so the speed will be very low. But if it is somewhere around 0.1 or 0.01, then it will be considerably faster. Okay, so that is just the alpha, that is the learning rate. It will determine how fast your gradient will move. So that's all that is. So now we have the previous W, right? So the previous W was somewhere around zero point 0.7, and then the alpha, let's say in this case, is 0.01, and then dW. And dW is nothing but what we got 2 slides ago, right? So we will replace all those value, and then we'll get a new W. Okay, and then we'll do the same thing for B, and we'll get a new B. Now again we will put both of these W as well as B in the new equation of the line, which will be y hat equals to Wx plus B. Now we will put this W as well as this B, the new ones. Okay, and then we will get some new y hat. Now we will check the error again. We'll check y minus y hat. Now we'll see how much the error is. Okay, now again, if the error is high, we'll do the same thing. We'll again go back to the update rules over here. We'll again calculate the derivative first. We'll again calculate the gradient first, and then we'll use the update rules to update W as well as B. Now then again we will get new values. So we'll get a new values for both W as well as B. Now again we'll put them in the equation of the line. Again we'll calculate the prediction, and then again we'll calculate the error. So basically this is an iterative process in which we will keep repeating the steps again and again up to a certain point where the error cannot be lower than it already is. So like let's say the error is 0.7 or 6 somewhere, and it cannot be lower than that. Now that will be your sweet spot where you will stop, where the gradient will stop. Either that, or you will specify some number of steps, number of iterations that you want to take, and after that the gradient will stop. But in either way your error will be reduced. So that is how gradient is calculated. Now we can also see a graphical explanation of this, and I'll draw that quickly. So you have, so this is your gradient, and let's say this is for your cost function, and then this is the initial point, correct? So this is the initial so these are the initial weights as well as biases. So for initial weights and biases, your gradient was over here, so this is nothing but the gradient, right? So it was over here. So this is not a good place to start. The error will be too high. So by doing all these steps, you will drop down to here. Okay, so now it will be calculated again. So the error will be considerably low than what it was before, but still exactly not what we desire. So further it will drop down, down and down until a point maybe over here. Now this is nothing but the global minimum. Now the error cannot be lower than this, because if it again moves past the global minima over here, then again the error will be high, right? So this is the sweet spot of the global minima. Now the goal for us is to reach this global minima by using all these steps, by repeating all these steps using the update rules. Okay, so that is what we need to do. Now, there is another method that you can try, which is called as a brute force. Now, if you ever cracked passwords, or if you basically done any of the information security stuff, you know what brute force is. So brute force is basically trying out every single value and combination until you get the right value. So basically we can try out all the combinations for W as well as B to find the sweet spot of the global minima to reduce the error. But yeah, doing this will cost you some millions and billions of years. So another galaxies will be formed before you can calculate your W and B and solve your equation. So that's why we use an optimization problem called as gradient descent, because the gradient descends in order to reduce the error and to find the global min and to reach the global minima, and hence we find the right values for both W as well as B, which then we replace in Wx plus B in this formula, y equals to Wx plus B, to find the y hat to get our prediction. So ultimately, by doing gradient descent, by following all these steps, ultimately you will get maybe something. So initially you had a line, I think somewhere around like this, but by following by using gradient descent, by repeating all those steps, actually I can use the same image. So by repeating all these steps towards the end, when your gradient reaches the global minimum, maybe you'll have a line which is something like this. Now this we can call as a line of best fit, while this isn't the line of best fit. So that is what gradient descent really is. That is like the optimization problem that we use to reduce the error. So that's what it is. Now obviously there are many variations in gradient descent, some of the popular ones being RMS prop as well as Adam. But like these are not entirely new techniques, they're all variations of gradient descent. So if you understand what gradient descent is, you can easily understand RMS prop, Adam, and some other of the optimization problems that we have. So yeah, that was it for this video. Hope you understood gradient descent a little more deeper than you previously might have. And if this video helped you in any way, make sure to like, subscribe, and share. All that good stuff that you need to do on YouTube. So yeah, I'll see you in the next one, hopefully. And yeah, take care. Bye.